Okay, in screencast number 2 for the guide sheet number 4, we're going to be looking at the rate at which the energy is changed as we go around the circuit. So we're talking about energy, the charge, the electrons are carrying the energy. They're going to be energized in the battery or power supply, and then whenever they go through some object, they're going to give off that energy in some form or another. So here's a picture of the circuit we're talking about. This would be the battery. This would be the 12-volt battery of your car, and this would be the resistor, those wires that run through the back windshield of a typical car. We're going to get the battery to heat those up, and that's going to help defrost the frozen precipitation from the back window of your car. So and this first question is: the charge flowing through the circuit possesses 0 joules of potential energy at point. Now, it'll possess 0 joules wherever the potential is 0, and the potential will always be 0 after it has gone through all the items in the circuit. So the answer here is actually point B, and then also to point A. Now, we make the assumption in that case that the wire has no resistance. In reality, it would be just before it went back into the battery at point A that we'd have absolutely no energy left, but to our ability to measure, points A to B would have no joules of potential left. Now, this particular circuit is using the energy of the battery. Now, batteries contain chemical energy, and we're turning that into something to defrost or get rid of the frozen liquid, so we're going to be heating it up. So what we're changing here is chemical into thermal in the long run. Now, the in-between step is to put that energy on the electrons and make it electrical energy, and then send it to the defroster so it can do its job. The potential energy of the charge at point A, again, it's approximately A and B are approximately equal. They're both essentially 0. We've used up all the energy by that point in time. The charge gains potential energy. Again, it will gain potential and potential energy as it goes through the battery. So a battery doesn't charge something, it energizes that charge. It gives it energy. So that's points A and D. And then when we go through something that's in the circuit, in this case the resistor that makes up the defroster, that's where we'll use up or lose the potential energy. So from point B to C. Again, the wires, we will assume that there's no significant loss within the wires themselves. Okay, now we want to spend the rest of the time looking at the rate at which that energy change occurs. The rate at which energy is delivered to a circuit by the energy source, or the rate at which energy is consumed, is known as power. So power is defined as the rate of work in basic mechanical systems, and it is the rate of energy transfer, since work is equal to the change of energy in our electrical systems. The unit of electric power is the watt, after James Watt, and 1 watt of power is equal to using 1 joule of energy every second. When we talk about power, electric power is the rate at which work is done on a charge. So it may be done on the charge by the battery to increase the energy, and then when it goes through, then that energy might be removed by that device. So a light bulb might turn the energy into light. A motor might turn it into mechanical energy, etc., etc. So power is defined as the rate of doing work. Now, work is equal to the change delta of energy. So we can also say that power is the rate of energy transfer. Okay, so as we do, it's the rate, how often, how many joules we transfer into some other form within our circuits. All right, so in equation form, it's work over time. It's also equal to energy change divided by time. Now, again, keep in mind that a watt is 1 joule per 1 second. So in letter A here, a 60-watt light bulb uses up, well, it uses up 60 joules of energy every second. If we multiply 60 joules per second times 3,600 seconds, we get 216,000 joules of energy being used in that 1 hour. And a 60-watt light bulb would only would use 4 times as much of that if we were to leave it on for 4 hours. So that's 864,000 joules, 4 times 216,000, if we leave it on for 4 hours. Now, a object that has much more power and uses the energy more quickly is an electric hairdryer. So a 1500 watt hairdryer would use 1500 joules of energy every second. So if we leave it turned on for 300 seconds, just like that, we are at 450,000 joules. Now you can see that's more than the 60-watt light bulb when it was left on for a full hour. So it was left on 12 times as much, but it still used up less energy. So more powerful items, things with a higher wattage rating, are going to go through energy faster, and they're going to transfer energy faster than objects with a lower power rating. Now 120 watt fans, a little bit higher than the light bulb and much less than the hairdryer. If we leave it on for a day, that's going to be 120 watts. That's 120 joules every second. There are 3,600 seconds in an hour, so we'll multiply that by 3,600. And then there are 24 hours in a day. So we have a really large number, 10,368,000 joules of energy on for that day. Now those are really big numbers to work with, so when electrical companies are looking to keep track of this electrical energy, they created a new unit called the kilowatt hour, or a different unit called the kilowatt hour, and we'll be looking at that in the future. Okay, so hopefully you can get the idea that power is the brings in this element of time. The more quickly we need to transfer energy, the bigger power we're going to need. Hopefully you can tie that into the lab where you crank the generator. The faster you crank the generator, the more work you were doing per unit time, the more powerful you were. The more light you should have gotten out the light bulb. It would have been the faster that the locomotive moved if you did the train test. So again, power is brings in the element of time. We'll wrap up with the matching in another circuit on the next cast. So that's it for today.